Okay, in this lecture, we will discuss convolutional neural network. We will begin our discussion by looking at object recognition problem. This problem has numerous applications and was a motivating problem for deep learning. In fact, the first deep learning neural network was created to solve the handwritten digit recognition problems for a banking application. So what is object recognition problem? The problem is simply defined as we are given an image and what we want our system to recognize or identify objects present in the image. For example, if we were to give the image shown in the slide to a system that performs object recognition, the system should come back with answers saying that there is a car in this picture, there are two traffic cones in the picture, and there is a football in the picture. So that's what basically the object recognition problem is. There are variations of object recognition problems. One variation or the simplest form of object recognition problem is what we call as object classification problem. In object classification problem, we just want to determine the predefined object type or category in the given image. This problem is also known as an image classification problem. As an example, look at a system that accepts an input picture and the system is supposed to come back with an answer whether the input picture contains a car or a sports utility vehicle or SUV. So in that case, we have two predefined categories, car and SUV, and system is going to look at an image and come back with an answer whether it has a car or SUV. So it will classify the image as a car image or as an SUV image. So that's basically the simplest form of object recognition problem known as image or object classification problem. Another problem or another variation of object recognition problem is what we call as object detection problem. In this problem, we not only determine whether a predefined object is present in an image or not, but we also locate the presence of that object in the image by drawing bounding boxes around the objects that are present in the image. As this picture shows, in this case, suppose our system has detected two objects. One is a car object, another is a motorcycle object. Then by drawing a bounding box around car, the system is telling us that there is a car object and this is the location of the car object in the image. And for motorcycle, again, it is telling us here is a motorcycle object and that's the location of the object. So as you can see, object detection problem has little more than image classification or object recognition problem. And also it provides bounding boxes, which is a useful information if one has to operate on information provided by the images. So that way we are getting little more information out of the system. Let's look at the next variation of the object recognition problem. This variation is known as the object segmentation problem. So in object segmentation, our objective is to isolate or mask those image pixels that are parts of a detected object. This problem is known as semantic segmentation problem. If you look at the left-hand side, topmost left-hand side picture, basically you can say in that picture we have three distinct types of objects. There is a person present in the image, sheep, and dog. And by putting bounding boxes around those objects we are performing object localization as shown in the right hand image at the top. If you look at the left hand image at the bottom, which is captioned as semantic segmentation, what we have done in this image is that we have gone beyond bounding boxes, and we have basically isolated all those areas of the picture, or all those pixels in these in the picture, which basically are part of the person, and we are showing those pixels by a different color. Then we have isolated all those pixels that are part of shapes present in the image, and we are coloring them with a different color. And then we have also isolated all those pixels that are part of the dog in the image, and we are showing them in a different color. Sometimes people want to make a further variation on the semantic segmentation problem, and that is known as the instance segmentation. So if we look at our picture, in this picture we have 5 instances of object sheep. That is, there are 5 sheep that are present in the image. In semantic segmentation, the pixels of all these 5 sheep will be colored with the same color, as we have done with blue in the left image at the bottom. But if we want to perform instance segmentation, then what we will do is, or what we expect from our system, is that the system should color different pixels belonging to different sheeps with different colors. So in this case, you can see in the right hand side image at the bottom, we have sheeps colored with different colors. So basically that will tell the system that, okay, there are 5 sheep and that's the corresponding location for these sheep. So obviously instance segmentation is more difficult. With that introduction of object recognition, and before going into further details, let us just look at images and refresh some of the basic background about images. So if you look at an image, or a digital image in particular, basically a digital image is nothing but a two-dimensional array of numbers, integer numbers, and these integer numbers are always positive numbers. The reason that they are always positive numbers is because the pixel values, or these numbers, represent the reflected intensity from the object. And since intensity is a measure of energy, so we can't really have negative numbers. So these numbers are always positive integer numbers. The array elements are known as pixels. And when you talk of color pictures, a pixel in color picture consists of 24 bits, where there are 8 bits per primary color. That means there are 3 primary colors, red, green, and blue. So there will be 8 bits for red, 8 bits for green, and 8 bits for blue. On the left hand side, on the right hand side, if you look at the image, basically I have shown you a very crude representation. That is, one can take this image and divide it into number of small rectangular blocks. And if you divide the image into n blocks going across and m blocks going down, then the size of the image is going to be m by n, and an element of the image could be represented as aij, where I will vary over 1 to m and j will vary over 1 to n. If you look at a particular pixel in a color image, so you can say that at that particular pixel location, we have three numbers that are associated with that location. One number is the number or intensity in the red channel. Then there is a number representing the intensity in the green channel, and there is a number representing the intensity in the blue channel. So if we look at our picture as a function f of xy, where x and y are spatial variables, that is, as we move around the picture, x and y values change, then function fxy can be represented through three functions: rxy representing variations in red across x and y, gxy representing variation in the green channel, and bxy representing the variation in the blue channel. So here is a representation, another representation you can say, just to give you an idea of how the color images are formed or how we look at color images. So the image at the bottom is the color image that you will see if you print it out or if you capture it with your camera. The image on the left in the top row is the image in the red channel. That is, if you were just looking at only the red parts of the image or red components of the image, that's how the image will appear. Similarly, in the center, you have the image in the green channel, and at the right, the image in the blue channel. And when we combine three of them, that is when you get the image at the bottom. So RGB, these three colors are known as the primary colors. And these primary colors are additive colors because when we add them, then only we get the color picture. Now, why is object recognition difficult? Or let's just try to gauge the difficulty of object recognition, because this is a problem that people have been addressing for the last 50, 60 years. And obviously, only in recent years, with the advent of deep learning, a very good progress has been made. So let's just get an idea of the difficulty of the problem. So here, what I'm showing you on the left-hand side is what we will see if we were standing in the street and looking at that picture or looking at that building. Now, if we use a camera and capture that, when we print out, obviously we see what we are seeing in the left image. But inside the computer, the picture appears as a collection of numbers, as we just saw in the previous slides. So basically, inside the computer, all we have is series of numbers. So to perform object recognition, what we have to do is we have to infer from these numbers what kind of objects are present in that image, or how the variations in these numbers represent a given object or represent different objects that we are trying to figure out. So that's really the object recognition problem. And as you can see, we have to actually jump from numbers to some objects that are well-defined concepts in our mind. So essentially what we are trying to do is to fill a semantic gap. That is, we have numbers, and from numbers we got to go to some concepts that represent different physical objects. So let's look at the earlier approaches to object recognition. As this slide shows, essentially earlier approaches consisted of creating handcrafted features and then using a large collection of examples, extracting those features, and then using those features as training vectors to train recognizers or to model and learn the distinctions between different types of objects or build classifiers. And once the training was complete, these classifiers were used to perform object recognition on examples that were not previously seen, or these classifiers were put into practice. The focus on early approaches was essentially on creating features that could help in identifying different objects at acceptable speeds. To give you an example of what kind of features were used, there is a feature or known as descriptors and more clearly known as scale invariant feature transform or shift descriptors. These descriptors, or there are several variations of them also, these are good examples of features used in early applications. Each image generates thousands of features. These features are also known as key points descriptors, with each feature typically consisting of 128 values. So on the right hand side, if you look at this picture, what we are showing you is the locations of these shift descriptors at different locations in the image. And essentially what these descriptors capture is the local variations in the image gradients. And those local variations are captured in the form of histograms. And those histograms then basically become the feature descriptors at different locations. These were very popular features, and they have been extensively used for many object recognition tasks. Let's look at how people were using image classification in the earlier research. If you look into the literature, you will find that both supervised and unsupervised learning methods, for example, support vector machine, decision trees, AdaBoost, vector quantization, etc., all these methods were used. The initial work was limited to few tens of categories. For example, people were doing character recognition or hand printed or machine printed character recognition. So obviously the number of categories there, including uppercase, lowercase, will be in tens of numbers. However, later systems worked with thousands of object categories or concepts. There was another approach that people followed for object recognition, and that was by creating specialized detectors that were capable of detecting presence of specific types of objects in the images. For example, in the left-hand image, you can see there is a detector that can capture whether there is a person in the image or not. So that detector has been applied here, and that detector is able to locate and recognize two persons present in the image. There is another detector that people built, and that's for detecting motorcycles. This is another example of detectors. Way back, people were building face detectors so that you could locate different faces present in the picture. So that's an example. And also people were building detectors for detecting different kinds of road signs. So the idea was that using these specialized detectors, one could perform object recognition or object classification problem. Now, these approaches, although gave limited success, these approaches obviously are suffering from several different issues. Two of the main issues are mentioned here. Number one, the features used in these approaches are manual or semi-supervised design of features. And such an approach is challenging because to come up with a manual feature, obviously you are dependent upon the creativity of the designer. And what people have seen is that coming up with features that are invariant to number of different factors when we talk about pictures, it's really difficult. And also, once people start using these systems, you want to perform object recognition for increasing number of categories. That means you need to continuously build more and more features to deal with increasing number of objects or increasing number of object categories. Now at this point you might wonder how many visual object categories are there. So let us try to make a guess, and this guess is based on the work published by a scientist called Biederman in 1987. According to his estimates, there are about 10,000 to 30,000 object categories that are of importance for object recognition work. So obviously, it is really difficult to come up with features that can help you to differentiate between such a large number of categories. So when we talk about building object recognition systems, we can say, why not we look at the best vision system that's out there for guidance. And that best vision system happens to be the one that we possess. And one of the characteristics of this system is that it is hierarchical, it's deep, and much of the system is the result of learning. So why not follow these characteristics and build deep trainable networks that use a hierarchy of trainable features going from low level to higher level of abstraction. So let's take a look at trainable feature hierarchy, which basically means hierarchy of representations with increasing level of abstraction. And each stage is trainable. And we can say each stage is a trainable feature transform. To give you an idea, let's look at the case of pictures where we want to perform image recognition. So we start with pixels, and from pixels we go to the next level of abstraction, that is grouping pixels into edges. From edges then we go to the next level of abstraction, that is textons, and from there we move on to motifs and to parts and the object. Similar ideas apply for text and speech. So if you look at the kind of scheme we want a series of trainable feature transforms that can be learned. And if you look at this picture, you can see that what we are showing you is the arrows are going back and forth. So how do we build trainable feature hierarchy? One way to do is through a pipeline of feature building via supervised learning. And this is shown in this picture over here. And this picture shows the basic building block for learning a single feature in the feature hierarchy. And there will be multiple such stages. Another way of learning is through what we call as unsupervised learning. And in unsupervised learning, we used a method or we used the kind of networks that are known as autoencoders. And these will be covered later in the lectures. So let's try to understand the different steps that are part of our basic building block for learning a single feature in a feature hierarchy. So the first step or the first stage in that building block I showed you in the previous slide consists of what we call as the normalization layer. The purpose of this stage is similar to the normalization performed on the inputs of a backpropagation network to make input values lie within a given range with zero mean, etc. And we have seen this earlier that if we do not normalize the input, learning can be slow, learning may not converge, and so on and so forth. So that's why it's important that we perform normalization even on the input images that will be fed to our deep learning network for learning the features and for learning to recognize between different objects. So here is a collection of images from a popular data set which is known as labeled faces in the wild. And that data set has been used by many researchers in deep learning to perform face recognition as well as for number of other applications. So this slide just shows you the normalization step, or at least the result of the normalization step using that face database I showed you in the previous slide. So the picture on the left basically is the mean picture. This represents the average or mean pixel values calculated over all the pictures. And of course, for every pixel location, we have the mean pixel value over all those pictures. The second picture on the right is basically again a representation in a picture form of the standard deviation of the data set that we are using in this particular example, that is the face data set. In Torch Vision package, which is a package that is part of the PyTorch library, and you will find that this package provides a variety of popular data sets for experimentation and benchmarking. This package also provides trained networks as well as models for use and repurposing. And again, we will be discussing these things later on. And also this package provides common image transformations for use with deep networks. You can learn more about this package by going to the URL mentioned here, which is of course from the PyTorch organization. So you'll be able to get a lot more information. What I'm going to show you here is a little bit of Torch Vision package use for performing image transformation, because that's what we are talking in terms of the normalization. So in the Torch Vision package, you will find Torch Vision transforms, which are basically manipulations or basic manipulations that the package provides to make on images so that you can put these images in a form and shape that is useful or suitable for inputs to the convolutional neural network models. And this package also allows you to put together a sequence of transforms that can be applied through a single step known as the composite transformation. So just to illustrate how this gets done, let's make use of an image. So there is a PIL library, which stands for Python Imaging Library. So using that library, let's read an image, and then let's display the image using imshow command. So here is the image of a mandrill, which is a color image that has been read. This slide shows you how to use this transforms from torch vision package. It just gives you one or two examples of using some of the transform operations that are available to you. The important thing to note here is that the PIL image is read as a numpy array, or you can say the output of the PIL image reading operation is a numpy array of size h times w times c, where h is the height of the array, w is the width, which basically means the image size, and c is the number of channels. For example, for a color image, c will be 3. And the pixel values are in the range of 0 to 255. When your PyTorch is going to be looking at an image as a tensor, it basically looks at the image in the form of a representation, where representation consists of c times h times w, where c is the number of channels, h is the height or the height of the image, and w is the width of the image. And all the pixel values are in the interval of 0 to 1. So once you read a PIL image and you want to use it with PyTorch, basically you can apply a transforms to tensor operation, and that will convert the image to a tensor representation suitable for PyTorch use. In this slide also I show you two other transform operations. One is the cropping operations and another is the random horizontal flip. You might notice that in the resulting picture, after applying the random horizontal flip, there is no flip. The reason for that is that this random horizontal flip or random vertical flip, these flips are applied with 50% chance or 50% probability. That means once you apply this flip, the flipping may take place, may not take place, and the probability for that is only 0.5. So that's why in this particular case, the flipping did not take place, and the image that you are getting is without horizontal flip, although you did ask for horizontal flipping to take place. Here is another example of applying an operation which is known as a transformation, that is random affine transformation, and the value in that small square is the angle value for affine transformation. So you can see that the transformation has taken place and the image is slightly tilted. Here is another example of showing transform operations. In this example, we are using two operations. One is the transforms to tensor and another one is transforms to normalization. And these two can be put together under a composite transform as shown in this picture. These numbers here are the mean values that are to be used in the normalization operations. And these numbers here are the variance values that are to be used for normalization. And once you have normalized and converted the image to a tensor image, if you want to take a look at that image and want to display it, what you'll need to do is to convert it back to a numpy array. So that step also is shown here, and what else is involved in that conversion is also mentioned here. So now let's come to defining what is convolution. Essentially, convolution is an operation on two functions of real valued arguments. One of these functions can be considered as one-dimensional signal, an array of numbers, or an image, or it could be a two-dimensional signal, and the other function is considered a kernel or operator. That means there are two functions that are involved. If you are talking of pictures, then Both these functions are two-dimensional functions. If you are talking of one-dimensional arrays, then both these functions are one-dimensional functions. Typically, one function is called a signal function, and the another function is called a kernel or the operator function. So let's look at a convolution example to understand what we mean by convolution. So let's look at a one-dimensional function f, and let's say that this function consists of a series of numbers 23, 12, 21, 22, 9, 11, and 16 as shown here. And let's define the other function, which is what we call as the kernel function. And you can see that kernel function is much smaller than the signal function, and it's always the case. Kernel functions will always be smaller than the signal functions. In this case, the kernel function consists of three numbers, 2, 1, 1. What are the steps that are involved in convolution? Number one, we will flip the kernel function w by 180 degree, and then we will align the center of this kernel function w with the pixel position in f, where we want to calculate the result of convolution. So in this example, I have highlighted the number 21 in one-dimensional function f. That is the position or location where we want to apply the convolution operation and calculate the result. So what we'll do is we will, as we have seen, we have flipped the w and we have aligned it with our 1D function at location 21. Now what we'll do is, to get the result of convolution, we will perform element-wise multiplication and then summation to get the result. So in this case, the result will be 12 times 1, 21 times 1, 22 times 2. That is this and this, this and this, this and this. And we add up and the number is 77. So the result of applying this kernel function to this particular position on this function is 77. Suppose you want to calculate the result of convolution operation at this location where the function has a value of 11 at the specified center location. So again, you can see that what we will do is we will basically shift this over here such that this center coincides here, and then the result will be 1 times 9 plus 1 times 11, so that is 20, plus 2 times 32, so result will be 52 at this particular location. You might say, all right, how about at the next location, that is at this location? You can see that when I place this mask over here with this point aligning with the 60, this element of the mask goes out. That means we cannot really define the convolution operation at a location where the mask elements are outside the range of the function. It is done, and we'll look at it how it is done in the coming slides. So let's move on. In 2D, let's take a look at an example. So suppose here is the input image we got, and here is our kernel function, and we want to calculate what is the convolution at this location. So what we will do is, again, we will flip the convolution mask as we did in the earlier case. In this case, the flipping will be done in both horizontal and vertical directions. And then, of course, in this particular example, since the kernel mask is symmetrical, so flipping is really immaterial. But strictly speaking, that is how it should be done. So once you have done the flipping, you place the mask over here, and then point by point you can do the multiplications. Since in this case most of the mask elements are 0 except these two, so basically the result of convolution at this place will be 3 times 1 plus 1 times 1, which is shown over here. And similarly, you can do the calculations at other positions. Now, what happens when we have color images? Again, this slide shows you how the convolution operation will be carried out for color images. So the operation is pretty similar to what we have seen. Only thing to note here is that in this particular slide, we are using identical filters for 3 input channels. And this is being done just for the convenience. In practice, each channel will have its own mask or its own kernel. So you can assume that for red channel, there will be a 3 by 3 separate mask. For green channel, there will be a separate mask. And for blue channel, there will be a separate mask. And calculations will be done for each channel using those masks. And then the summation will be, and then the result will be placed in a single output array. Another thing to note here is that the 3 input images here, or the input image here is an 8 by 8 size, and the mask size is 3 by 3. The result of the convolution operation in this case is a 6 by 6 result. And the reason for that is that when mask is placed at the first row or first column, obviously part of the mask goes out. So that's why the starting position for this mask in this case has to be at this place, at this place, at this place. And this mask will be moved all the way up to here, then like this, all the way up to this point. That's why you get the 6 by 6 result instead of 8 by 8 result. So that's basically what we call as convolution at edges. And to do the calculations, as we did in the previous case, we did not do any padding. So basically our result was from an 8 by 8 input, we ended up with a 6 by 6 result using a 3 by 3 convolution mask. Sometimes you can do additional padding to the image, and with that padding you can get the result similar in terms of the size, similar to the input size. For example, if this was our 8 by 8 image and I padded it with extra 2 rows, 2 columns in both top and bottom, left and right, then this becomes a 10 by 10 image, but all the padded elements have 0 values. In that case, now if I apply a 3 by 3 operator, a convolution operator, the result will be an 8 by 8. So this is what we call as 0 padding. And of course, to do the 0 padding, sometimes people don't use 0 padding, but rather use what we call as periodicity assumption, which that means is that you can take this 8 by 8 image and assume over here there is this image is repeating, over here this image is repeating, over here this image is repeating. So in that case, basically you can place your convolution mask even at the edges. That means you can get the result which will be of size 8 by 8. And of course, if you don't use 0 padding or do not make the periodicity assumption, your result will be cropped result. That is, it will be smaller in size than the input. And how much smaller will depend upon what is the size of your kernel mask. Now, these kernel operations are actually linear operations on images. And many operations on images can be described in terms of moving a specific mask or kernel over the entire image, pixel by pixel, as we have done in the convolution operations. The kernel entries determine the kind of resulting image. And two such major linear operations are known as correlation and convolution. So basically these operations are defined in terms of a mask. So this will be kernel mask or convolution mask. And here you can say it's your image. So as we saw previously, you will take this mask, place it at different positions one by one, slide it over the entire image, and for every position you will be calculating the results. The difference between correlation and convolution is that the kernel mask is applied directly in correlation, while in the case of convolution, the mask is flipped. So if this was the kernel mask, this will be applied directly as it is if you were performing the correlation operation. But if you were to do the convolution, then this will be flipped horizontally and flipped vertically. And this is the mask then that will be used for convolution. This is another picture illustrating how correlation and convolution operations will be carried out. This picture essentially shows again the flipping of the convolution mask, while in the correlation there is no such flipping takes place. Mathematically, if you were to define, you can define these operations through these discrete summation operations. Now, one thing to note is when the kernel is a symmetric function, then correlation and convolution are identical because flipping does not produce new mask values because of the symmetry. Now, in deep learning, when people talk about convolution and they talk about the mask or the convolution mask, basically you will find that people are not doing any flipping. So technically speaking, convolution in deep learning is really a correlation operation. But somehow or other everybody has started calling it convolution. So basically that's what we will do. We will call it convolution too. But technically it's a correlation operation. Now let's look at some examples of convolution operation to give you an idea of why convolution can be used for building features. So let's take a look at a function f of xy. In this case, it's a gray level image. And let us apply on that image a convolution operation using this mask. And you will find that the result of applying this mask on that image turns out to be this image. Now, if you look at this image, you will notice that the horizontal branches of the tree are much more highlighted in this image compared to the previous with respect to the image I showed you in the previous slide. So that means what this particular mask has done or the property of this mask is to highlight or pick up those parts of the image or those edges in the image that are sitting more or less horizontally. Let's look at another mask and let's see the result of using this mask on the same image that we used in the previous slide. So in this case, you can see that this mask has highlighted all the vertical edges. So in this case, this mask is highlighting the vertical edges. Now in this case, we have taken a random mask. This is another example of a random mask. And in this particular case, you can say that this because of the random mask, the highlighting of the features, it's kind of little random in this case. We cannot make a definitive statement that only the vertical edges have been highlighted, or the diagonal edges have been highlighted, or the horizontal edges have been highlighted. Here is another example of a mask. This particular mask is known as a Laplacian of a Gaussian mask, because if you were to visualize this mask, this has a shape or a form that looks something like this. This matrix represents the weight values of the mask. Mathematically, this is how the mask is defined. And on that particular picture, if we apply this mask, basically that is the result we get. And in this case, you will find that what this result is showing is it is highlighting all the edges, whether they are vertical, horizontal, or diagonal. So this mask can be used to extract all the edges in an image. The basic idea of showing some of those results using 2-3 different kernel masks was to show you that by applying different mask weights and different kernel sizes, one can enhance different properties that are present in the image. Or in other words, one can perform feature extraction using these kernel masks with different weights and different size. So with this, we'll stop here and we will continue in the next lecture.